This mini lecture is about complexity theory, or we could talk about dynamic systems theory in nature. Within complexity theory, we can distinguish chaotic complex systems, chaos theory, as well as self-organized systems. We'll get into the particulars in a couple minutes. But complexity theory in general tells us about the interconnectedness of things, and it emphasizes holism, how the whole of a system is not just the sum of the properties, the behaviors of the individual parts. We've already seen some of this interconnectedness, some of this holism in our discussions last time about relativity theory, even before that, electromagnetism, and then with quantum mechanics. Now, complexity theory deals with larger scale phenomena, but electromagnetism and force fields also deal with larger phenomena. Relativity theory does too. That applies to the macro world, the world we live in as far as what we can perceive. Against the mechanistic view that things tend to be separate billiard balls that just kind of interact more or less externally in absolute space and time. We've seen how time is relative, somewhat relative, to how fast one thing is moving in respect to something else. We've also seen, in terms of how some things affect other things, how general relativity tells us that space is curved and that the mass of an object influences the space and how things behave, how they move in relation to each other. And then on the quantum mechanic, the microcosmic levels, we've seen, or at least implied, that there's holism in terms of when the parts of an atom come together, the individual components, electrons, protons, neutrons, and an atom literally means that which can't be divided, but and Dalton discovered that in the early 1800s. Then by the early 1900s, we realized, no, that atoms are not literally atoms. They're made up of smaller particles. But as Barber writes very perceptively, when these particles, which are also made up of smaller particles, like protons and neutrons, are made up of mesons. So they're not just fundamental particles, but they're interrelated, connected in a whole with yet more fundamental particles. But anyway, when the protons, electrons, and neutrons come together, it's not like this new configuration, this atom or this molecule has the same properties of the individual parts, that you could add them together. As Barber writes, the wave function of a helium atom is very different from the wave function of its components. The electrons there are no longer behaving as individual, independent electrons, but like a two-electron system where they can't be distinguished as individual electrons from each other. So even in that small scale, the whole is much different than the individual properties, wave functions, structures, and so on of the parts. And if you just like add an electron, a neutron, and a proton and get another element, one up on the periodic table of elements, the properties of that next element up can be completely different, extremely different from those that just have one less of each particle. So there's a whole lot of holism going on the atomic and molecular levels. Okay, so now we're going to get to complexity theory itself. And I'll note that Alfred North Whitehead, who was a great mathematical physicist before he became a great philosopher, he's the one who developed process philosophy and theology. Barber, our most important author, because he gets into those four models that we should be thinking about when we talk about any of this scientific stuff in relation to religion: conflict, independence, dialogue, and integration. Well, Whitehead invented process philosophy and theology, which is an attempt really at integration, at trying to come up with a metaphysical or religious system, a total system that is compatible with modern science. And Whitehead admitted this is speculative, it's imaginative, but he was doing his best to try to integrate science and religion, science and metaphysics, the philosophy of the ultimate nature of all things. As Whitehead looked at the history of science, in natural philosophy and natural science, he noted how the model of organicity held from ancient times through the Middle Ages, and we've talked about this earlier in the semester. And then with the Enlightenment and Newton and everything, mechanism, right, comes in. But with the developments of the 19th century and early 20th century with electromagnetism, relativity, quantum theory, we're back to organicity and the holism of organicity, where the whole natural world, the whole universe, is an organism in which different parts contribute to a greater whole. All right, so now let's get to complexity theory itself. Whether we're talking about self-organizing systems or chaotic complex systems, we're talking about an interplay of order and disorder, orderliness and disorder. All complex systems in some way can be approximated, at least in theory, to non-linear equations. And linear equations are ones that kind of correspond to this absolute space and time, this whole mechanistic thing where there's a simple equation that you can solve. But nonlinear equations are much more complicated. And for chaotic systems, they involve iteration, where you have a particular constant and a particular initial value. We can call it x0 or xn, if we, depending on whether you wanted to use numbers or letters. And then say you have this constant k times xn times 1 minus xn, and an example here on the printout, if any of you hopefully have gotten that up or printed it out. Each iteration takes the value from the last iteration in this ongoing process. And so we can see that it's that if it's based in this equation, that it's not completely disorderly, right? There's a clear mathematical equation that the natural, chaotic natural systems at least approximate. Now, the general assumption is that these equations are deterministic, so chaotic natural systems are deterministic. But as Polkinghorne notes, that is really a metaphysical assumption. So he believes that it may be that these formulas are only approximations. I guess you could say they have some probabilistic dimension to them. So there may be some openness in these chaotic systems that seem in some ways very random, like the weather. To us, it often seems extremely random, but it's definitely not completely random. And in speaking of that, in chaotic systems, folks talk about strange attractors. Well, what are these? Basically, if we imagine the ongoing states through time of a complex system, and just plotted them on a piece of paper, on a computer, and they're absolutely random, there'd be no obvious pattern at all, right? But in fact, chaotic systems do congregate, we might say. They're attracted to certain points or areas, and these are called strange attractors. And we'll talk in a minute about fractals. But these strange attractors, the states, the iterative states, the ongoing states of this chaotic system form a pattern around these strange attractors. So they're clearly not completely random. They are unpredictable with these nonlinear equations. If we were able to measure these things, which we're not, then we could see if they really conform deterministically to the equations. But the deal is with these equations that they are unpredictable. Even if they're deterministic, we'd only be able, if we had to put it into a computer, we'd only be able to predict it for a few iterations, for a few moments in time, and then it would overwhelm the computer's capability to calculate the state further on in time. So if it's deterministic, and we have an all-knowing mind like God in traditional theology, well then God would know all the future states of a chaotic system, again, if they really are deterministic. Now, I mentioned fractals. A fractal pattern is one in which each part of even if we kind of look at it geometrically, if it's something solid that we can kind of plot or see geometrically, we'd see that each part is the same pattern as the whole. Each smaller part is the same pattern as the next larger part and the whole part. We can see this in a chaotic system, which would be on coastlines, on the sand in relation to the ocean, and how that all interplays. It's chaotic, but it's not totally random, and these smaller patterns are there within the larger coastline patterns. So that's a chaotic system. We can also see this with trees, which are not chaotic systems. They're self-organized systems. They're biological systems. But anyway, we can see the fractal pattern that is going on. in the kind of shape of the tree overall, then the limbs, then the smaller limbs, the twigs, even the roots have this similar kind of pattern. And fractals or strange attractors always are fractal. Now, this may not always be visible like it would be in something very visible like a coastline, but the repeating patterns of the states are fractal. We also do chaotic or create a chaotic system when we mix dough. Certainly we can't do the same thing or need the dough. It would not work if we did the same thing. But actually, it's not totally random. We kind of wrap things around and kind of, in some ways, each smaller thing is kind of maybe fractal with mixing the dough. But we're, actually doing this chaotic, complex system when we mix dough. So you can do it, folks. All right. Some of you have heard about the butterfly effect. If you remember, we did talk about it. So if you were in that class, hopefully you do remember. And actually, sometimes strange attractor patterns themselves look like butterflies, but it more particularly refers to kind of a thought experiment, we might say, that a butterfly flaps its wings in China, and that could lead to a thunderstorm, say, in North Carolina several days later. And just last night, around 8 o'clock on April 8th in North Carolina, we had a warm day and we had a thunderstorm. So chaotic systems are very much susceptible to small changes in their initial conditions. So the condition at any given point in time, well, we can imagine how the weather pattern in China, if that butterfly hadn't gotten as in part of the weather pattern, this whole weather pattern, versus with the butterfly in the mix of this chaotic weather system. And just these systems are very sensitive, and we talked about how these patterns just a little ways into the future are totally unpredictable or extremely unpredictable. So a small difference in an initial condition can make a huge difference much later on. So in theory, at least, something, butterfly flapping its wings in China could make a huge difference in North Carolina much later on in a state of this weather system. This chaotic system, as well as complex theory, system theory in general, tells us about the non-isolability, the unisolability of complex systems, that they are embedded, relate to other complex systems, whether self-organized or chaotic. So again, that interconnectedness of things. Systems are not able to be completely isolated from their total environment. All right, enough about chaotic systems. So complex chaotic systems, and there are some non-complex chaotic systems. But let's talk now about complex self-organized systems. What happens here is sometimes when you have a lot of disorder where the state of something is far from equilibrium, meaning very unstable. We can talk about, as we did with evolution, about how difficulties in the environment, dangers, lack of needed resources in an environment can create a situation far from equilibrium for an organism. And you might recall from when we read about evolution in Barber that he talked about complex systems there. Well, what happens with self-organization is sometimes when you have these unstable situations where things are very random, far from equilibrium, if there is sufficient energy put into that disorganized, not so complex system, it can self-organize into a complex system. So from disorder at a lower level, you have a new higher level order that's stable, that reaches equilibrium. As with, crystals, you have at the lower level just the minerals, the rocks, but some of them are, if there's enough energy, are able to crystallize and have a very definite, sometimes for us, a beautiful pattern that can remain for an extremely long time. Biological systems are self-organizing systems, and we already talked about that some when we talked about different ways to understand what might be happening with evolution. And so biological organisms involve this coming to the first life we can imagine, fairly random elements far from equilibrium were able to self-organize into the first molecules of life, a higher order. And we also talked about how there does seem to be some, at least many would believe, there is some top-down causation in the sense that it's very much the case that the properties of the whole, the self-organized system, are different than the sum or any just combination of the individual properties of the parts. The whole is greater, it has a greater order, and has different properties than the sum of the parts. So there's something you could talk about, a sense where it's kind of a mutual causality. The lower elements exercise some causality, the self-organization, the top level organizes some causation, but it's not the case that the lower level just determines things in a totally mechanistic sense, a linear sense of just adding up the properties of the parts. And so, we come back to the question of it with self-organized biological systems, especially with animals and most especially for us humans. Is there any indeterminacy in terms of our ethical, our religious choices, or is everything ultimately predetermined? Well, again, if there are equations that govern, very set equations that govern the behavior of self-organized systems, these systems that are stable, or relatively stable for long periods of time, then we'd have to say no, they're unpredictable, but they're still predetermined. There is no such thing as free will in the sense of indeterminacy. right? That you can really tip the balance. You're torn between maybe enjoying something, a pleasure or social sharing with others, but maybe something about this, especially in the time of coronavirus, might damage your future health. So you're torn between two possible values, right? Two values. Do you tip the balance, or is it ultimately determined by some equation that operates in this self-organized biological system? So we're back to the nature of consciousness. But complexity theory does at least have religious implications in terms of the interconnectedness of things and the holism, that we're not just isolated monads, individuals, but we are in ourselves a holistic system, and we're within larger holistic systems.